Good morning, everybody. So welcome to this last day of the ETAPS conference, at least for the main conference. So it is a great pleasure for me to introduce the ETAPS Unifying talk of Professor Rupak Majumdar. So I first met Rupak at the end of the 90s when I was visiting the group of Tom Enzinger at UC Berkeley. So Rupak has done his PhD there. Then right after that, he was an assistant and associated and full professor of computer science at UCLA. And in 2012, so he joined the Max Planck Institute for Software Systems in Kaiserslautern, and he's a director there. So Rupak is a very well-known researcher in our community, so he has done plenty of very nice contribution. And his research covers a large number of subjects. So he has, for example, done a lot of contribution to the algorithmic verification and synthesis for models like hybrid systems and stochastic systems. So he's one of the pioneers of software verification. So you may, or you should know about BLAST, so which was one of the first efficient tool for verifying software. So he's one of the developers of this tool and the theory behind it. So he has also done a large number of contributions that are more fundamental and that are in logic, automata theory, but also games for synthesis of controllers. And so, the main application that he pursues is the rigorous development of cyber physical systems. And so today we'll share his vision about future challenges in the development of cyber physical system, but now with human in the loop. So, Rupak, the floor is yours.
Thank you. Thank you, Jean-François, and hi. It's an honor to be here as the invited speaker at ETAPS. So I will talk to you about robots at the edge of the cloud. And the way it all started is that at some point, my kid, who was, I think, 6 or 7 at the time, came to me and said, you know, I saw a really cool movie about a guy who's a scientist like you, and this is very pleasing for a father, but cooler. And I said, what do you mean? Well, he said, well, he builds cool stuff, like robots and stuff, instead of, you know, writing in notebooks and checking email. And this I found very insulting. I told him, look, I work in robotics. I've read all these books. And not just that. I've been writing all these papers. These are all about robots. And frankly, you know, if this doesn't scream robot to you, kid, I don't know what will. But he wasn't convinced. I guess what he had in mind was this. And I told him that, look, this is Hollywood nonsense, don't believe this. Do you know that this guy is not even Indian? But the poll numbers were in, you know, in the 100% of the 6-year-olds in the family thought that dad was uncool, and I had to do something about it. And I wanted to out-robot every maneuver of this guy. And what I will tell you are some of the research challenges that we have to meet before we can do that. Okay? So I will start with a few well-known trends in computing that I'm sure all of you know. The first is the Moore's law. So this says essentially that every 18 months or so, the transistor density doubles. And this has essentially led to an exponential growth in computing capabilities. Okay? The second graph that I want to show is a similar graph in terms of our communication bandwidth capabilities. And again, the key point here is that if you look over the years, there's an exponential increase in our communication capabilities. Finally, here's a third graph that shows that the number of devices that we are connecting to the internet has a similar exponential growth. And by some estimates, by 2020, there'll be about 50 billion devices connected to the internet. And many of them are sort of mobile devices like mobile phones and so on. But a very large fraction of this are sensors, right? Sensors with some microcontrollers that can connect to the internet. And so we are at a confluence where over the last 5 years, we are seeing tremendous drops in the cost of bandwidth, in the cost of processing, and in the cost of sensing. And what this has led to is a large number of applications where you have edge sensors that are somehow measuring the physical world or the ambient world, and mobile devices that are connecting through some gateway device to the cloud, which is essentially a very large distributed computing capability, computing and storage capability. And what we are seeing are applications, mostly in consumer analytics or real-time sensing and monitoring, that are somehow sensing the real world, communicating wirelessly over a large network of computers, doing a lot of processing, and analyzing the data that they sense. But this is only one half of the story. The other half of the story is that we are seeing more and more edge actuators that can come back and influence the real world in various ways. And we are seeing a large number of applications starting to be developed that close the loop in this sense. So there are edge sensors that sense the physical world. There's some communication and computation in the back end. And then there are actuators that come back and influence the world. Okay? And there are many examples of this kind of systems. For example, process automation, closed-loop decision-making, and complex autonomous processes. For example, autonomous vehicles or autonomous transportation networks. And the potential of these applications is enormous, both in the compass of their applicability and in terms of business values. And it is not hard to see that if we can build these systems in a safe and in a reliable and in a cost-effective way, they have the potential of transforming many different aspects of our lives. Okay? So in this talk, I will essentially talk about some research and design challenges that would let us design this kind of sense, compute, actuate applications in a reliable and safe way. Okay? And I will keep this talk more or less at a high level. I will tell you about a few things where we have made some progress over the last few years. But I would also like to point out that this area is actually very wide open. So if you are intrigued by some aspect of what I'm going to talk about, I would be very happy if we are able to collaborate, both individually and as a community. Okay? And feel free to stop me if you have any questions in the middle. Okay. So at the core of these kind of sense, compute, actuate systems is something called a feedback controller. And I will quickly give you a very brief introduction to what this means, because as computer scientists, control is usually followed by alt and delete. But essentially, there is a field of control theory that looks at the problem of sensing some physical dynamical system and then figuring out how to influence this dynamical system to achieve a certain behavior that you would like to achieve. So you can think of you come up with a model of the physical world, which has both continuous components and discrete components. You can sense the state of the physical world. You can do some computation. And based on this computation, you can send back inputs to this dynamical system so that your overall system has some nice properties. Okay? And in general, these nice properties traditionally studied in the field of control theory were things like robustness or regulation, where you would like to check that a system stabilizes under some uncertainty in its environment, or that it tracks some reference signal. But there is a more emergent view of control just as a collection of tools and techniques for designing and implementing these kinds of complex, interconnected dynamical systems. And there are essentially two trends that we see more and more. The scope of control goes beyond just the dynamics at the lowest level to managing the interaction of the entire system, and in fact, to the entire enterprise. And the second is that, as you very well know from from formal methods, that if you want to manage a system at various layers of granularity, you have to come up with suitable abstractions to model each layer. Okay? So that's where we'll start. So we'll look at certain abstractions that you can do in building up these large classes of systems. And at the lowest level, what we are looking at are at the dynamics level, we are looking at systems modeled using differential equations. The specs are, as before, stability and performance or regulation. And here, you can use methods from classical control, like PID controllers or LQR control, and so on, to manage how to get the performance or stability that you need from your dynamics. But we'll go further up the level. At the next level, you can think of this as a component level, where we have the dynamics interacting with discrete modes of operations and under potential uncertainties. And the specs at this level could be things like temporal properties that you would like to enforce on the system. Okay? And at the component level, you're probably going to use the lower level classical controllers to do single steps, but then you would like to chain these steps together somehow in order to make sure that your system satisfies more complicated properties. Okay. At the next level, when we have multiple such components, the main problem is that of coordination. Most of the work here is really at the discrete level, and where you're trying to coordinate the actions of multiple control systems, which in turn may have complicated temporal logic controllers that depend on PID controllers, and so on. Further up the level, we will talk about sort of large-scale software services that talk about, for example, global distributed properties of a large software system, such as provisioning, scheduling, fault tolerance, and so on. And really at the very high level, you have these kinds of cyber-physical systems that are working with humans in the loop, that are interacting with humans in a very non-trivial way. And here, really, I think the field is completely open, right? So at the end, I will have a couple of slides on this, but this is what we would really like to design. We would like to design large-scale software and and physical systems that also interact with large number of humans in a non-trivial way. Okay, so this would be essentially the outline of the talk. And in order to motivate what we are doing, I will start with a platform that's called the TurtleBot. So this is a very cheap robotic system that you can buy. This essentially consists of a little platform with a Kinect sensor that can let you sense in 3D where the robot is. It has some motors and so on, and it has an open source software stack. So it's a very nice platform for playing with some of these ideas. It's not as impressive as a robot that my kids saw, but that's a separate story. So as I said before, at the lowest level, the controllers on this robot will be the kind of traditional LQR or PID controllers. But around it, we will talk about how to build algorithms for doing temporal logic control. On top of the temporal logic control, we will talk about some hierarchical abstract controllers that make sure that you can look at the control problem at various levels of abstraction. And then we will talk about coordination between different agents. Okay? So this is the problem where you have multiple robots that have to somehow collaborate in order to do some activity. So this is more at the algorithmic side. We will also look at some challenges in the implementation of the control algorithms that we come up with, as well as problems arising out of controller and system co-design. Okay. Now, at the next higher level, I will talk a little bit about some system services that you really need to do if you're building large-scale systems of this nature. And finally, as I said at the end, I will talk a little bit about challenges if you want to incorporate human behavior. And in some sense, as we go higher and as the background gets lighter, the less I know about these problems. Okay? Okay. So this is the outline. If you have any questions, stop me at any point. So I will give you the marker along the way to show you where we are in the stack. Okay? So we'll start with temporal logic control. Okay. So here is the problem. So I have some system that I've modeled maybe as a differential equation or as a discrete time continuous state system. So there is some state variable x, which is in general some n-dimensional real number, real vector. And X is a dynamical system, so X evolves according to some dynamics law that we have written here as some function f of the state of some control input and then of some disturbance. And the disturbance may be stochastic. And the Q here is some discrete state, because in general, this differential equation may have different modes according to some discrete automaton that it interacts with. And the problem that we'd like to solve is that given a system of this form, I would like to synthesize a controller that satisfies a temporal specification on the discrete and continuous dynamics. Okay? And for specificity, let's say that this temporal specification will be given to me as a linear temporal logic formula or as an automaton. Okay? Now, in general, if these disturbances are stochastic, of course, you would like to get this controller with stochastic guarantees rather than, or probabilistic guarantees rather than deterministic ones. I should point out that the verification problem in this setting is already a very hard problem, and it could be the basis for an entire talk. But what we're interested here is to essentially look at correct by construction or synthesis techniques that would help us build controllers for these kinds of systems. Okay, so let me just talk about let me quickly summarize why we are interested in this discrete constraints. Well, they actually arise as soon as you try to build non-trivial systems with software-enabled control, right? So traditional control theory looked at purely continuous time systems, but in the systems that we are trying to build, discrete constraints come in many forms. For example, these could be like these temporal constraints on the behavior of the system. There could be multiple modes of dynamics in the system itself. There can be resource constraints, for example, scheduling constraints that tell you when you can or cannot run the control loop as a software task. There could be coordination, there could be layering and abstraction, and so on. Okay, so the main idea here is essentially this kind of an abstraction refinement loop, where what we'd like to do is we'd like to start with a continuous system, and we'd like to abstract it to some discrete system. And if we can, once we have a discrete system, we have this entire field of reactive synthesis for linear temporal logic properties that we can use in order to take a discrete system and find a controller to enforce a temporal property. Okay? Now, at this level, we have a discrete controller. What we'd like to do is we'd like to have a refinement process where this discrete controller can be refined down to the continuous and discrete system by essentially providing the control input U. In general, the way this would work is that the discrete controller that you get from the reactive synthesis will essentially give you a sequence of commands that would tell the dynamical system to go from one point in its configuration space to the next. And these would be dealt with some of these lower-level LQR controllers, for example. Okay? So now the question is, what is the appropriate notion of abstraction? Okay. So if you come from the process algebra world, you would say, well, you should look at something like bisimulation or simulation, because these relations tell you when exactly you can preserve behaviors between the original systems and their abstractions. And essentially, this is what we'll do, except that because we are working in this continuous domains, exact bisimulation is usually too precise a notion, and we will not be able to use that in an effective way. But the idea that Girard and Papas came up with in about 2007 and followed up by a lot of other people is this idea of epsilon bisimulation. So the idea is that, you see, most all these systems are in some metric space. So X and Y, there is a metric D that you can define on the system space. And the notion of epsilon bisimulation essentially says that I want the 2 points to be close to each other. And then whenever one of them makes a step, I want the other to follow as well so that they're again close to each other. Okay? So this is captured by the metric here. And as you can imagine, and as you can show, if you follow this, the usual notion of bisimulation and so on, in this context, you can show that if this is true, then for every trajectory of the system that you can get from x, you can get a trajectory from y that is always at most epsilon away. Okay? Well, okay, bisimulation is not quite what we want. We really want something called epsilon alternating bisimulation, because this is the generalization of this notion for games. And what we'd like to do is preserve controllers across, a concrete game and an abstract game. And so this notion of epsilon alternating bisimulation was introduced by a paper by Rajiv Allur, Tom Hensinger, Ona Kupferman, and Moshe Vardi. And then its epsilon or continuous epsilon version was studied by Girard Papas and others. And again, you don't need to go through the definitions. All you need to know is that if I can come up with an abstraction like this, then I can take controllers that I get in the abstraction and refine them into the concrete system. Okay, so that's very good. So we will use these epsilon alternating bisimulations as our notions of abstraction. The question is, when are we guaranteed that this continuous system will have a finite state bisimulation equivalent abstraction? So for this, there is a notion of incremental stability that was studied in control theory for some time that seems to be of help. So incremental stability is informally the property that if you run the system, then the trajectories of the system converge to each other. Okay, so for example, if you start your system from these two initial states and you let the dynamics evolve, then under an incrementally stable system will ensure that these trajectories converge to each other. And you can, you can define this notion of input to state stability because we also have the control input. And again, if you understand this notion pictorially, then you really do not need to look at the formulas. Okay? So, if you know about linear systems, asymptotic stability implies incremental stability. Okay, and the intuition behind the abstractions is actually very simple. What we'll do is we'll discretize the input and the state space. And so under the assumption of incremental stability, what we can show is that the error that you accumulate by mapping every state in this blob to one of its corners goes away as you run the system, because under incremental stability, the trajectory that you get from here will converge to the trajectory that you get from there. Okay? So this is the basic intuition why this works. And the rest of it is really algebra. What you need to find out is that once you have fixed your precision epsilon and let's say some sampling time tau, you have to carefully come up with the discretization parameters of the space, of the state space and of the input space, so that by looking at the properties of the incremental input to state stability, you can ensure that the discretization is small enough that you get a finite epsilon alternating simulation. So this result is actually the basis of an abstract controller synthesis methodology that I showed you. You start with a continuous discrete system, you abstract it, you compute a controller using discrete techniques, and then you map it back. And there are several symbolic tools for controller synthesis that you can use. There are some of them, like Pessoa, that are directly based on this observation, and then there are many others that have come up in the last few years, and not all of them use this kind of discretization the way I mentioned, but all of them internally have some notion of reducing the problem to reactive synthesis and getting a controller out of this. Okay. So far, the systems that I talked about were deterministic, but you can play the same game for stochastic systems as well, right? So here I have modeled the continuous dynamics as a stochastic differential equation where the evolution of the state depends on the state and the input, but also some stochastic noise. Okay? And what we would like to do is, again, play this game of coming up with an abstraction to a finite state discrete system, doing reactive synthesis there and putting the controllers back. And at this point, you really have two options. You can abstract to a deterministic system that is guaranteed to preserve moments, And the other is you can preserve distributions and go instead to a probabilistic system. And actually, we have tried both. And the basis for the first one is a generalization of this idea of incremental ISS to incremental stochastic ISS, where you require that the trajectories converge in expectation or in the qth moment. And in fact, with my student Majid Zamani, we studied this notion of incremental input to state stability in the qth moment and showed that it has nice properties in the sense that you can again characterize them using Lyapunov function-like characterizations that are known also, known for deterministic systems. So essentially, it works very well, generalizes quite well to the stochastic setting as well. And with my former student Majid Zamani, who's now at TU Munich, we could prove a similar result. Well, for the stochastic system, the result is somewhat weaker. It says that for each compact set U, you can find a choice of these discrete parameters A and B such that there is a finite stochastic epsilon alternating by simulation. I mean, okay, the term is a little bit long and scary, but all it tells you is that if you only focus on a compact region of the state space, you can play this game again where you start with a stochastic system with continuous dynamics, and you can go to a discrete system such that if you build a controller in the discrete world, you can push it back to the continuous world. Okay? And so as an example of what these things would look in practice, you could imagine that you have some kind of robot which is an orange square, not really a nice robot, and you want the robot to go to some other place in the presence of obstacles, and this kind of controller synthesis methodology would give you a controller that would find a path of the robot. And in this particular simulation, you see that the abstraction had about 90,000 states, and the abstraction procedure took about 10 minutes to run. And the control design took around 3 minutes using this tool Pessoa that I talked about. Okay. So these things do not scale very well at this moment. The main problem is the curse of dimensionality. But at least for some small examples, we can do this, run this methodology of abstracting, doing reactive synthesis, and then pushing the results back. An alternate direction is where you want to preserve distributions, and some of this work is done by my postdoc Sadek Surjani, who is in the audience somewhere, where you start with a continuous stochastic system and you abstract it to a probabilistic system that is epsilon probabilistic bisimilar. So I guess this idea was first looked at by Alessandro Abate, Gius Peter Katun, John Ligeros, and I forget the first name of Prandini, in a 2010 paper. And since then, we have started to look at results of the following form, where you start with continuous stochastic dynamics, you abstract it out to a finite state Markov chain or a Markov decision process, and under the assumptions on the dynamics of the original system, you try to prove some formal bounds on the error that you accumulate by this abstraction. Okay? So essentially, you can under the Lipschitz continuity assumptions, you can find some discretization parameters that when you go to this discrete Markov chain, then you're guaranteed that the behaviors of this abstraction stay within epsilon of the original system. Okay. So this is all I wanted to talk about temporal logic control, just to give you an overview of the kind of results that we have done here. Now let's move up a little bit in order to look at some problems in abstract control. As I mentioned before, these abstraction techniques and these controller synthesis techniques are expensive, and the expense goes up as you have more and more dimensions in the state space. But what we can use is really a natural hierarchical decomposition that is present in many of these problems. So for example, think again of this robot motion planning like example that I showed very briefly. Now, if you're thinking of a robot moving in a building, there's a very natural decomposition of the games that you can solve. For example, you can solve a game at the level of each floor of a building. Within each floor, you can solve the game for each room. And within a room, maybe you have a sort of discretization of the state space, of the continuous state space that you use in order to get the controller in that room. The whole point is that if I were to model the entire game at this level of granularity for the entire system, our tools just do not scale. On the other hand, when we are solving the game for the robot in this room, maybe we can really abstract out what is going on in the other floor. I mean, not always, but under some situations, you can do this and get good controllers. Okay? So this is what my postdoc, Anne-Catherine Schmuck, has been looking at. So you can use the underlying metric structure of the problem in order to get a natural hierarchy of games. And now what you can do is that you can come up with dynamic controllers for each layer. So essentially, what you would like to do is you would like to solve a game at each layer of the system, and in some sense, at each tick of the system. Okay? So the reason you want to do it at each layer is that, well, at this floor level, I can have a specification that only talks about requirements at this level of granularity. I can ask the robot to go from this floor to that one. Now, this specification that only talks about this layer can lead to obligations at the lower layer. If I know that the robot is here, I know that in order to go to this other floor, it must go through these rooms and then go up the stairs. Okay? So a specification at the higher level leads to a specification at the lower level that you need to solve. And in order for the robot to satisfy this specification, at the lowest level, it knows that it has to go from this point in this room through the door to the next room. Okay, so there's a natural decomposition of requirements as you go down the abstraction. And moreover, these things can change dynamically. For example, if the robot finds that this door is blocked, then it can send this information up to find a different strategy at that layer to accomplish the requirement at that layer. Okay? And moreover, in addition to the requirements that you get from the higher layers, you may have requirements at the lower layer as well. So for example, maybe the requirement is that go from this room to that one, but along the way you have to, I don't know, collect bottles or serve coffee in each of these rooms. Okay? So you get a sequence of games that you have to solve dynamically and online, but each game is in this abstract and smaller arena, and then you have to compose everything together. So if you know about model predictive control in control theory, this is kind of a model predictive control, but not just in the time horizon, but also in space. Okay, so I will talk a little bit about coordination, because this problem is very related to the kind of abstract game solving that I just talked about. And the idea here is that if you have multiple such robots, and if you have environment assumptions at each layer, how do you synthesize controllers compositionally? So each agent may have a spec phi. Now, one thing you can try to do is that you can imagine the paranoid robot who thinks everybody in the world is trying to kill it, and you can solve the game of one robot against the entire world. Unfortunately, if you do this, most of the time, even for very basic tasks, you will come up with there is no controller. Okay? Now, the point is that if you have two robots that are running around in this building, they're not really actively trying to kill each other most of the time. Okay? So what we'd like to do is come up with a notion of synthesis under assumptions. And actually, we were stuck at this point for a very long time until we saw this paper that Jean-François had with some of his collaborators last year about setting up this problem as something called an assume admissible synthesis problem. And this was exactly what we were looking for. So you can think of this assume admissible synthesis as a generalization of assume guarantee reasoning to the synthesis setting. Okay? And this is what we are now implementing. So let me quickly give you a demo of what this looks like, if it works. So again, we have these two turtle bots, and we have this kind of assume admissible controller that's running in the background. And the tasks are actually very simple. We have marked some positions, and each robot gets a stream of requests to go to one of these locations, right? So they kind of patrol the area where they get dynamically these requirements to go to a certain next spot. Okay. So that's all I wanted to talk about control design algorithms. What I would like to do now is switch a little bit to talk about software issues. Okay, so we are looking at software issues and systems issues at two levels. The first one are challenges that come up in just implementing the control algorithms on a real system, on a software stack. And there I will just briefly talk about two challenges. The first one is that connecting the mathematics of control to implementation in software. And the second is the co-design problem of controllers and platforms. Okay? And then I will go up a level in the abstraction, and I will talk a little bit about the software stack for these kinds of swarm autonomous systems. Okay, let's focus on the first one. So here is the problem. So in the ideal mathematical model, which uses God's real numbers, you might be able to prove that a controller ensures that the dynamics is of a certain shape. For example, your ideal mathematical model can say that the dynamics eventually converges to the origin. Now, in the implementation, you will probably not get this ideal behavior because the software may not match the math. So in software, you're probably using limited precision arithmetic. You have some quantization of the sensing and the actuation. You have a whole lot of software-related effects that were probably not modeled in the control models. And so what can happen is that the implementation can behave somewhat differently from the ideal world. So the implementation may not converge to the origin, but it may converge to a ball that's around the origin. And the problem that we would like to solve is that can we link the math of the control theory world to some analysis on the software, so that we can say that the software that you implement, the software controller that you implement, gets close to what the ideal world tells you, and we would like to get a quantitative bound on how close it gets. Okay, so we would like to get a bound on rho. And here we got this result, and this is in collaboration with Adolfo Anta and Paulo Taboada. Paulo is a control theorist at UCLA, and my former student Indranil Saha, whose dissertation was on this topic. And we get a very nice separation of concerns theorem of the following form. So I'll just state the theorem for linear control systems. You can get similar results for nonlinear systems as well. And the result is very simple. If A is the L2 gain of a linear control system, and you can think of the L2 gain as a measure of, if you perturb the inputs, how much the system can be perturbed, and B is a bound on the implementation error, then this rho, how close you get to the ideal behavior, is bounded above by the product of these two terms. Now this is nice because this A, the L2 gain, is essentially a property of the mathematical model that you're looking at. And B is a pure program analysis problem. It just says, I give you an implementation, how close is it from some ideal specification? Okay. And so Indranil worked out a specific example of bounding the error that you get out of using finite precision arithmetic. And the idea is that, well, in many sort of microcontrollers, you implement floating real-valued computations using something called fixed-point arithmetic, where each real variable is implemented as using an integer which has n bits, of which k are used to model the fractional part. Okay? And once you have a representation like this, then you can perform arithmetic operations approximately using bit shifts and integer arithmetic. Okay? So what Indranil's thesis showed, and there are a whole bunch of other works as well on bounding the numerical error in computations, is that you can come up with a static analysis to compute bounds on the numerical errors due to fixed point arithmetic. And now if you put these together and use the theorem, then you can essentially give an end-to-end guarantee of what the actual implemented controller would do in the behavior of the system. Okay, and so this is the verification problem. I give you a specific controller, and I ask you how close does it get to. But you can ask a corresponding synthesis problem where you explicitly ask to find a controller that minimizes this error. Okay? And this you can again do by modifying the standard control design procedures like LQR control to explicitly track an implementation error term. Okay. There is a slight complication here. LQR control, like things reduced to nice convex programming problems. But once you start adding these implementation error terms, then the problem that you get is non-convex. But on some examples, we explicitly model this kind of implementation error, and you could get controllers that were within 10% of just the LQR optimal controller, but with a much better error bound, right? That arises because of the implementation fixed point effects. Okay, let me talk quickly about a second problem, and this is about connecting the software tasks that you get out of the controllers to the rest of the system, okay? And so we are still here. And the point is that at the control theory level, you have a plant, you have sensors, actuators, and you have a controller that you compute. That senses the state of the plant, computes some control input, and puts it back to the plant. Now, when you implement this controller, this control task becomes a piece of code that you're running on your system. And the sampling rate that you have at the control theory level becomes a timer that says that this piece of code must be run at a certain period, okay? And this is just for one control loop. In your system, there can be multiple control loops that you're trying to schedule on the same shared infrastructure. So there could be a shared CPU, and then there is an operating system scheduler that's sitting there, and it knows that there is a task here that should be run at a certain rate. There's another software task that should be run at a certain rate, and so on. And the relation between the rates and the control is the following. So control theory tells you that here's a computation of the control that you should do based on the sensed state, and you have to do it at this sampling rate. And if you do this, then I guarantee you that that control loop has some nice properties. Similarly for this one and for that one. The real-time operating system does not know anything about what you are doing or what this controller is and so on. It just knows that here's some piece of code, and through some analysis, it figures out how much time it takes to run. And it just knows that this piece of code must be run every tau1 time units. Okay? Similarly, this other piece of code that takes that much time to run should be run every tau2 time units, and so on. And in general, there is a brick wall between the control theory world and the OS world, right? So the operating systems people do not like to talk to the control people, and vice versa. Well, it's changing, but to a first approximation, this is the case. Okay? And the entire behavior of the system is guaranteed if you can match these schedulers. And this is the sort of real-time scheduling problem. I give you a bunch of tasks. Can you schedule them? If you can schedule them, go ahead and do it. If you cannot do it, well, send it back to the systems developer, or get a faster CPU and so on. But what you can actually do is you can co-design the controller and the scheduler by saying that suppose I relax the problem by letting you drop some tasks every once in a while. Clearly, then you can schedule more things because every once in a while you can drop a task. But if you do this too often, then you're in trouble because then the controller may not have the right properties, right? You're running the system in open loop for a long time. But what you can do is you can essentially factor these kind of drops when you're designing the controller. And this has traditionally been studied in the network control system world where people have looked at controllers that are working under sort of network drop constraints. And you can essentially prove theorems of the following form, that suppose I have some control system where the controller may or may not be computed at each cycle, at what rate, what must be the minimal rate that you have to guarantee in order for the control system to satisfy properties, like be stable or have a certain performance. And once you do this, you can come up with a relaxed schedulability problem with task drops, where you essentially ask that I have all these tasks, and for each task, I also tell you a rate at which you can drop them. And then what you want to do is you make sure that in the long run, the scheduler does not drop tasks more than that fraction. And what is interesting to us is that this is essentially a real-time scheduling problem with a liveness constraint. Most scheduling problems are really safety, right? Because you can show a finite execution where the deadline is violated. But this is a long-run average kind of property, and I think this was not studied previously in the real-time systems world to a large extent, and maybe some of you know more. Yeah? Okay, so let me now pop up a level to systems and software services. So that was all I wanted to say about sort of the programming issues of the controllers and the systems at the low level. Now, I don't want to say too much about the programming models because I think if you were at the other invited talks, they did an excellent job about talking about software abstractions, and many of those ideas really carry over to this world as well. But what I would instead like to do is talk about some system services that would be useful in this world. And let me give you an analogy from the world of analytics. So if you know about things like Apache Spark and so on, so you can think of these as distributed databases. So there is a data model, so you have a lot of data that lives as tables in a relational database or as streams or as key value maps and so on. And at the user level, you have a query language like SQL, let's say, for databases, or some streaming query language or some statistical model that you're interested in. And then there's a runtime that says, I will manage this data for you, and whenever you have a query, I will answer this query and return it to you. And this runtime is really a black box as far as the user is concerned. Now, in order to implement this black box, you have a lot of software components. You need some core engine to sort of distribute tasks. You need some sort of MapReduce framework. You need a storage system to handle these MapReduce jobs. You need a cluster manager. You will need something that does fault tolerance, and so on. But at the level of the user, this is a completely hidden thing, right? So the user says, I have a declarative language where I tell you what I want. I have a data model that tells me how to evaluate, what results you should expect, and system, go do it. This is a very nice abstraction. You have a model, you have a spec or a query language, and you have a runtime that takes care of many of the software services for you. What we'd like to build is essentially a similar model of services for the kind of autonomous systems that we're looking at. So the data model probably is going to be some version of the hybrid dynamical systems that I showed you, some combination of continuous and discrete systems. The query language at this point, we're using LTL. It's not really suited. We would have to come up with a declarative way of saying what is the global property that we need from the system. We have to come up with query evaluation, which sort of compiles this down into the individual requirements on the autonomous systems. And then the runtime should really manage everything else. It should synthesize the controllers, it should manage the robots, and so on. Right? So this is the first step towards the drone army. Yeah? Okay. Now, what I would like to say is that at this point, there is a gap here. So for the individual turtlebot that I showed you before, there is something called the robot operating system, which is essentially a messaging layer on top of the operating system services that lets you do stuff for one robot. And on top of it, we are now implementing these controller synthesis algorithms to move the robot from here to there and so on. But even if you try to put several of these together, you will very soon see that the software is very flaky. And what is really missing here is this link between the sort of low-level operating system features that you have on single bots to an overall software system that manages bad robots and so on. Okay? And so this is what, again, we are building. So with my student Ivan Gavran and my former student and collaborator Jeff Fisher, we are essentially building this kind of software services in the middle. So we are building some kind of software layer that sort of handles these multiple robots. We are managing some sort of provision manager that checks if the robots are okay or not and sort of distributes control tasks and so on. At this point, the query language that we have is a very simple data parallel LTL. You can think about this as saying, here are some tasks, and you can map each of these tasks to one of the robots. And the only interaction is that the robots should not bump into each other. Okay? But this is really the vision, right? And we are very early in the process. I can show you a very quick demo of what this looks like. So this is the old example that I had, but now notice that this guy has crashed. Now this guy was supposed to go somewhere over there behind this shelf, but because it has crashed, the swarm manager at some point has to notice that this robot is out of commission, and then it has to distribute its obligation to this other one. So you will see that while before the other one was just traveling here, this time it has to go there in order to make sure the other spec is also met. Okay? And this has to be done really at the software service level, because robots will crash. They are really flaky. And if you are managing a whole bunch of them, then you don't want to do this by hand. Okay. Okay. Okay, so this is all I wanted to talk about software. Now let me talk about the broader context of building these systems in the sort of social context as well, and well, this is left as homework, right? But okay, more seriously, I think I can give you a whole bunch of problems here. Unfortunately, these are really hard problems. We have made no progress on this at all. I will just list a few of these problems. These are things that we are looking at now. How do you build this CPS in a robust way with human in the loop? And the first question is that if you're building these kinds of systems, what should be the specification formalism? I can tell you, through personal experience, humans are very bad at satisfying temporal logic objectives. If you have been in a faculty meeting, okay, let's not get there. So while it's perfectly fine for us to do all this kind of temporal logic synthesis for autonomous systems, well, the way you model, the way you get humans to collaborate to do something is really in this kind of other game theory, right? Which is sort of game theory arising out of economics and mechanism design and so on. So really, if you want to have a system where the humans are interacting with these autonomous systems, you have to come up with some way of giving specifications to each part so that they combine well together. Unfortunately, the communities that do this kind of temporal logic game solving and communities that do algorithmic game theory do not often talk to each other. And as a first step, we are organizing a Dagstuhl workshop to try to bring these communities together to see if there are commonalities that we can exploit. But again, I think this is quite an interesting open area that we do not know how to deal with. Similarly, if you're thinking about doing systems design issues, how do we model humans? How do we test these systems? I mean, it's bad enough for developing CPS. It's very difficult to test these things and get them right. Now, if these systems are interacting with humans, it's actually a very difficult software engineering problem. And then there are much harder problems about social aspects of human autonomous system ensembles. How do you deal with privacy? How do you deal with trust in these systems and so on? And again, I think these are much harder problems that we would probably get to after we have some handle on the first parts. Okay, so let me conclude. So I think what we are doing now is we are building a world-sized robot. So we have the internet that connects every aspect of our life. We have a lot of computing and processing power in the background that we can get to very quickly. And we are building these systems that are navigating and influencing our world through sensors and actuators with these large computation and communication capabilities. And building this robot reliably really requires solving fundamental problems in the theory and practice of software. Okay? So this is essentially all I want to say. I should just leave you with one final word. So while as people working on technology, we are really interested in building cool technology, cool stuff that will enable these systems, there is, of course, a sort of dual side to it about the users of this technology. So I don't know if you have followed an invited talk that Phil Rogoway gave last year, as well as an initiative that Stuart Russell has with a bunch of AI experts. And this is to make sure that we as computer scientists understand the social responsibilities of building these systems. While it's very nice for us to have these turtle bots running around, very soon somebody is going to put a gun on one of these things and on many of these things. Right? And if you haven't already, I would encourage you to look at these two, the invited talks and the position papers. I think both are excellent. Okay, so that's all I have to say. This work has been done with a whole bunch of excellent collaborators. I have listed some of them here, and thank you for your attention.
Thanks. Very nice talk. So, questions, remarks, opinions? Yes.
Thank you for the inspiring talk. So many more connections than I sort of saw before. So what I would like to ask is there any connection between this hybrid hierarchy that you talked about at the control level and the cloud services? So if the problem naturally decomposes, maybe you can figure out and put some parts of it into the cloud. For example, the map of the building doesn't have to reside in the robot, or something like that. So how do you coordinate those two things?
So I think we are a little bit too early to give you a very good answer there, right? We are still sort of building some of these things and trying to see how well they work. But I agree, and this is essentially the point that I would like to make, that there is a sort of control that you can implement on an individual system, and then there is this computation, communication in the back end that you can use. And what is the right trade-off in designing a system, I think at this point is very open, right? And we are doing something very trivial in the sense that for us, yes, the map of the building is in the cloud. The robot kind of connects to it to know the local map at each point. And the cloud essentially at this point for us is just the coordination mechanism, right? It will check if the robots are doing okay. It will sort of take a task from the user and schedule it to the robots. But we have not played that much with what part of the control itself can you move to the cloud and what can you do there. So these are open.
Do you see any need or room for using machine learning somewhere in your picture? I was thinking you're basing your synthesis on models. Where will the model come from? I mean, maybe they should be learned. Maybe even in the synthesis you could do some, enforcement learning.
Yes. Ladies and gentlemen, I've definitely not paid him for this question. It's a true statement, but it sounds bad. Okay, but yes, so my point is that, yes, of course, like machine learning is the sort of elephant in the room. And to me, this is not an either or, right? So machine learning works very well, and in some sense, if you're using a robot, you're using machine learning just for the navigation stack. It has these Kinect sensors. From the Kinect sensors to the map of the world is a machine learning thing, right? So, but I do not see this as an either-or choice that we do either completely formal reasoning or completely learning. But I think the research challenge is essentially to figure out how to get interfaces between them to allow us to reason about the system, right? So this is really the crucial part. Some part of it will be statistical, some part of it we will do algorithmically, and the question is how can we manage the interaction between the two. Yeah.
Any
I wondered if your son is now suitably impressed.
Sorry?
I was wondering if your son is now suitably impressed.
It's very difficult to impress 7-year-olds.
Okay, so any additional question? No? So let's thank Rupak again. So I have a present from the ETAPS organizers, and I have also a small